Okay, so good evening, students. Again, this is Dr. Zhong. Today, we are going to continue our discussion of dynamic programming. So last week we just had took 1 week off basically because I don't give you any new video lectures as well as new homeworks. So hopefully that you got more time to capture what we have already learned, and also be well prepared for the midterms in your other courses. So for our course, there is no midterm. Okay, so last time we learned the dynamic programming. So we see that dynamic programming is pretty much like divide and conquer. It's a philosophy. It's a design philosophy that can help us to reduce the time complexity of an algorithm. And the key logic is that okay, if for any program, if we want to use dynamic programming, we need to check if the program shows the optimal substructure property. The optimal substructure property means that the optimal solution to a big problem incorporates the optimal solution to its sub problems. Okay, last week we learned the first problem that can be resolved by using dynamic programming. It is the rod cut problem, and giving a rod of length n, we basically want to find the best way to cut it so as to maximize our revenue. So and mathematicians or those people who are pretty good at math can help us to formulate the solution to the rod cut problem into this way. Okay, it is Rn equal to so the max from 1 to n. Okay, it is pi plus Rn minus I. Okay, so this means that if we are giving a rod of length n, we are now, instead of thinking about all the possible cuts, let's just think about the leftmost cut, which can make our problem for definition a little bit easier. So here we can say that let's make the leftmost cut at a place named I, so that we divide a rod of length n into two parts. The left includes a small part of length I, and the right includes a part whose length is n minus I. So because on the left this is our leftmost cut, so we are not allowed to further cut it. So then the revenue, or the revenue that we can make from the left is just fixed. It is pi. Pi tells us, okay, how much money can you make by selling a piece of rod whose length is I directly without any cut. And for the right part, yes, we are allowed to make as many cuts as necessary. Since its length is n minus I, the highest revenue that we can make from it is just Rn minus I. Okay, and here we basically enumerate all the possible places of the first cut from the first place to the last place, and then we basically want to say, okay, which first cut gives us the highest revenue, and then we will pick that. So this is the formulation of the problem. And here I want you to, the thing that I want you to note is that on the left hand side, we have the solution to a problem whose size is n, and it includes the solution. It incorporates the optimal solution to a problem whose size is n minus I. Since I is a positive integer, so n minus I is definitely less than n. So here we can say this is a solution to a big problem, optimal solution to a big problem. And on the right hand side, we say this is the optimal solution to a sub problem, or to a small problem. Okay, so this shows the optimal. This shows the optimal substructure property, which is the optimal solution to a big problem, incorporates the optimal solution to its sub problem. Okay, so and in this case we can use dynamic programming to reduce the complexity of the the problem solving procedure. And the idea is that instead of just say giving a problem, instead of just directly working on the problem, we we basically check if we have resolved this problem before or not. If yes, then we don't need to work on it anymore. We just retrieve the solution. Otherwise, if it's a new problem, then we just work on it and then store it at some place for future reference. In this way, we'll be able to reduce the complexity. And if you remember, in the route cut problem, if we don't use dynamic programming, the complexity is 2 to the power of n, and here we just reduce it to the complexity of 2 to the n squared. And so this is a major improvement in terms of time complexity. So hopefully you can feel the power of route cut problem from that. Okay. So, and today we're going to explore dynamic programming, but now we're going to work on a more difficult problem. The problem is more difficult because mainly because so we have different layers of for loops. But actually, in my opinion, it is easier for you to understand because this example is more interpretable. Okay, so the problem is that given two strings S1 and S2, and we basically want to find the longest common subsequence between them. So what is the longest common subsequence? I'm just going to give you an example right over here. So suppose here we have two sequences, X as A B C B D A B and Y as B D C A B A. So the longest common subsequence is just a sequence of characters that show in both X and Y, and also they show in the corresponding order. So here the longest common subsequence between X and Y is BCBA. So because we have BCBA in X, we have BCBA in Y. Okay, so here you may note that the characters in the longest common subsequence do not have to show consecutively in the original strings. It's not necessary. As long as they show they follow the order, it is fine. So this is the longest common subsequence because we cannot find any common subsequence that is longer than this one. Okay. So here you may think, okay, let's think about it. Let's think about it in this way. Okay, let's say, what if we include one more character from them? Let's say not BCBA. Let's use BDCBA. Let's try to say if we can just increase the length of this common sequence by 1, and here I'm just giving you an example by inserting a new character D between B and C. So here we can say BD, yes, only BD only shows in this way. So BDCBA does not even show up in X, but we have BDCBA in in Y. Okay, so if you have time, you can just try to you can just enumerate other possibilities and find that BCBA is the longest common subsequence between these two strings. And another example is here. Okay, so here you may say, okay, this problem is not too difficult. You can just work out the solution by yourself by taking maybe 2 minutes or 5 minutes at most. But what if I just increase the length of the input strings to a very large number? So here we have two strings, S1, S2, and our objective is again to find the longest common subsequence between them. So yes, of course, this is way more difficult, and you may take at least an hour to figure it out. And this is actually the longest common subsequence between S1 and S2. So So if you are familiar with if you are familiar with biology, you probably know that what are these? These are just DNA sequences. S1, S2 are just DNA sequences. So, like probably you heard about that. Okay, so if there is a criminal, if there is a crime, we just collect the blood of the something, and then we may have a few suspects, and here by using the DNA by comparing the DNA, we will be able to figure out if the suspect shows up in the scene of the crime, and this is the place where we should use longest common subsequence. Okay, if the longest common subsequence between two DNAs are pretty long, there is a big overlap between them, we are pretty much sure that yes, they are at least the relatives, or not, if not the same person. Otherwise we can say they don't have a strong relationship with each other genetically. So okay, and let's formulate the problem, formally define the problem in this way. So the input is that we have two sequences, x and y, so their length are just m and n. So m and n are the number of characters in x and y respectively, and our output, so we want to find the length of the longest common subsequence between x and y. If possible, we also want to discover, okay, what is the longest common subsequence between x and y. Okay, so that is our objective. Given two strings, we want to find the length of the longest common subsequence. So, and here, just some mathematicians work out a theorem to show that the longest common subsequence problem also adhere to the optimal substructure property. So they just define this prove this theorem. Okay, so here let me just tell you, okay, what does this theorem mean? Okay, so it means that here we have x with x1, x2, xm minus 1 and xm, and we have y, y1, y2, yn minus 1, yn. Okay, so here we have two strings, and so this theorem tells us, okay, if the last character of these two strings match, so if xm and x and yn match, if they match, then the longest common subsequence, so we call it z between these two characters, okay, would be this way. Okay, it will be the longest common subsequence between the first m minus 1 characters between of x, and the first, I'm just going to use the capital character to denote a substring, okay, meaning that the first couple of characters. So it will be the longest common subsequence between x and y will be the longest common subsequence of the first m minus 1 characters of x and first n minus 1 characters of y, plus the last matching one. Let's just call it zk. Okay, zk is the same as xm and yn. This means that, okay, if we find a match at the last position, we're just going to include that in the longest common subsequence, and then search for the longest common subsequence between the first couple of characters of x and y. Okay, so then the concatenation between them will be the longest common subsequence between x and y. Okay, so this is the This is the this is one case of the theorem, the first case of the theorem. And also here you can see that here basically we want to, if we want to find the longest common subsequence between S1 and S2, since they match at the last character, we just include the matching A at the end, and then find the longest common subsequence between the first. So without by excluding the last character, we just search for the longest common subsequence and do a concatenation between them. Okay, so so this is the what the first case of the theorem says. And here let's just look at another case. Okay, so what if so previously we discussed that, okay, if they match, if the last two characters match, the last character of the two strings match, but what if they don't match? What is the longest common subsequence between them? So in case there is a mismatch between the last character, okay, in the last character, then we need to do it in this way, okay? So either we exclude the last character from X, so we basically search for, we just basically search for LCS X m-1 and yn. It's like we basically exclude the last character of X and then search for the longest common subsequence between X and Y. Or we just we can do a similar thing. Okay, we're just going to exclude the last character of Y. Okay, we just delete that and search for the so xm, the first m characters of X and the first n-1 characters of of Y. So and then search for the longest common subsequence between these two substrings, and then so whichever we will take whichever is longer as the longest common subsequence between X and Y. Whichever is longer between these two, okay? So yes, this is what this theorem tells us. If there is a match in the last character, then we just take the matching character and then search for the longest common subsequence in the first m-1 characters of X and n-1 characters of Y. Otherwise, we just exclude either the last character of X or the last character of Y, and then search for the longest common subsequence and find whichever gives us a longer one, and then we will take it. So this is what the theorem tells us. And then these mathematicians so go one more step by giving us a very cool mathematical formula. So here we have the mathematical formula presented in this way. Cij is this. Cij is the let me just define Cij. Cij is this, the length of the longest common subsequence between the first I characters of X and the first j characters of Y. So Cij is the length of the longest common subsequence between the first I characters of X and first j characters of Y. So here let's look at this formula. Okay, if I equal to, if I 0 or Y 0, if I is 0, it means that there is nothing. It's just empty. So we got an empty string in X. Or if J is 0, it means that we got an empty string in Y. So here if you just try to find the longest common subsequence between an empty string and any other string, the result will be just an empty string, right? And the length of the longest common subsequence will be 0. Okay, so this is the first case. It means that if either subsequence is empty, then the length of the longest common subsequence would be 0. It's pretty easy to understand, right? So then let's look at the second case. If xi equal to yj, it means that here, let's consider the first I characters of x. Let's just consider the first I characters of x, xi and yj. So we have x1, x2, xi minus 1, xi, y1, y2, yj minus 1, and yj. Okay, what it says is that if the last character match, then according to the previous theorem, what we will do is that we'll just take the matching character, and then find the longest common subsequence between the first I minus 1 characters of x and the first j minus 1 characters of y, and then concatenate them, okay? And this is what this theorem tells us, okay? If I and j are larger than 0, and if the last character match, then we will just take the matching character, okay? So that we will just have this 1. So it means that we append one character into the longest common subsequence, and then we will just take the length of the longest common subsequence between the first I minus 1 characters of x and first j minus 1 characters of y, and then add 1, which is the last matching character, okay? So otherwise, if it is if both I and j are larger than 0 and xi and yj does not match, the last character does not match, so what we said is that we will just either eliminate the last character from x, or eliminate the last character from y, and then take the longest common subsequence and take whichever is longer, okay? So here it is. Here we just take the last character from y and search for the longest common subsequence. And now in this case we eliminate the last character from x and search for the longest common subsequence. Whichever gives us a longer LCS, we will just take it, okay? So this mathematical formula is basically just a very, very natural or straightforward translation from this theorem, okay? So if you understand the previous theorem, coming to here, it's not too hard for you to understand the formula, okay? But just in case that you don't understand it from the perspective of a programmer, it is absolutely fine. It's okay, because your job is not to derive this formula. Your job is to translate this formula to algorithms or to programs, okay? So that if you are able to understand the logic of this formula, that is perfect. If not, it's fine, okay? It will not say be a problem for you to do your homework, okay? So then let's look at this mathematical formula. On the left hand side, we have the optimal solution to a problem whose size is I and j. So here we use two integers to define the size of a problem. I means the first I characters of x, and j means the first j characters of y, okay? So, and on the right hand side we have this I minus 1, j minus 1. So the problem size on the right hand side in this case is I minus 1 and j minus 1. Over here it is I j minus 1 and I minus 1 j, okay? So what we can see is that on the left hand side we have the optimal solution to a big problem whose size is I and j, while on the right hand side we have the optimal solution to its sub problem whose size is I minus 1 j minus 1, I j minus 1, I minus 1 j, okay? So here it is a optimal solution to a big problem incorporates the optimal solution to its sub problems. Again, this shows the optimal substructure property. And so let me just write down the mathematical formula for the route cut problem here. So hopefully that you can find something in common. Rn equal to the max. Okay, here we can see that the optimal solution to, so in the mathematical formula of the rod cut problem, on the left hand side we have the optimal solution to a big problem whose size is n. On the right hand side we have the optimal solution to a small problem whose size is n minus I. Again, it shows the optimal substructure property. So in case you find this property, okay, in case you find this property in a problem, or if you see a mathematical formula like this where the left hand side is the optimal solution to a big problem, and on the right hand side we have the optimal solution to a small problem, you should definitely consider using the dynamical programming to make your program more efficient. Okay, so this is the our mathematical formula, and starting from the mathematical formula, we will need to have this pseudocode, and my task today is mainly to explain this pseudocode to you. Okay, so but before that, I just want to briefly talk about your future job interviews, your potential job interviews. So so in your job interview, definitely at least one of the problems. So usually you will have six. Usually you will have six programming questions. Like each programming question is like an interview and takes around 55 minutes to 1 hour. So at least one out of the six questions will be dynamical programming, and it is going to be extremely challenging. According to my personal experience, this is the most difficult one. So it's the difficulty lies in how can you derive this formula and realize that it shows the optimal substructure property, and then realize that you need to use dynamical programming to solve it. So typically in a job interview, your interviewer would not expect you to derive such formula by yourself in maybe 10 minutes or 15 minutes. So instead, they will help you to reach the formula like this over here, okay? And then starting from there, it is totally up to you to show your programming skill and your programming logic. So that's why I said it's very hard, because you only have 30 minutes to realize that so you need to use dynamical programming and then design the pseudocode as well as translate it to either Java program or Python program. So this is really challenging. So spend your time on it on this topic. Okay, so and this is the pseudocode of the LCS problem. So I'm just going to give you a couple of minutes to go through it and think about it. Okay, so let's look at the pseudocode. So in the first two lines, we just get the length of the two strings in the variable m and n, and then we just create two tables. So by table we mean they're just two-dimensional arrays. So we create array B and array C. So let me ask you one question. What is the size of B? It is m by n. So then the size of what about the size of C? It is m plus 1 times n plus 1. This is because the index of C starts from 0 rather than 1. And then we just have something, okay, so for I starting from 1 to m, for j is and then for j starting from 0 to n, we do something, okay? And then we have the main part of the algorithm is here, okay? So so we have I starting from 1 to m and j starting from 1 to n, if, else, and else. So, okay, so let's look at the pseudocode together by using an example. And the example would be here, okay? We have x and y as here. So, I'm just going to clean this up and then create a new one. Create a, sorry, this is the hour slide. So, okay, here we are going to have two input strings, x as a, b, c, b, d, a, b. We have x as a, b, c, b, d, a, b, and y as b, d, c, a, b, a. Okay, so here let's look at the pseudocode. First we have m equal to the length of x, which is here. Let's just do a count. We have 7 characters, so we have a variable m as 7, and then we have n equal to the length of y, which is 6, so we have n as 6, and then we just create 2 arrays b and c. So the size of b is just m by n, so we are going to create an array whose size is m by n. So this is b, and we have 2, 3, 4, 5, 6, 7, and 1, 2, 3, 4, 5, 6. Okay, so the size of b is just m by n, 7 by 6. So we have the index as 1, 2, 3, 4, 5, 6, 7. This is because the index of in b starts from 1. Okay, so 1, 2, 3, 4, 5, and 6, and then we just, so here we need to create another array c whose size is m by 1 and m plus 1 and n by n plus 1. One, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. Okay. This is a little bit ugly. I'm going to redraw it. So we have, so here the index in the array C starts from 0. Okay, so we have 0, 1, 2, 3, 4, 5, 6, 7, and 0, 1, 2, 3, 4, 5, 6. Okay, so and then so let's go to the first for loop. For I starting from 1 to m, so I starting from 1 to m and ci 0 equal to 0. So initially we have I as 1 and I can go up to 7. Okay, so here when I is 1, we have c10 as 0. So where is c10? C10 means that so we are going to use the first index as the row index, and we use the second index as the column index. Okay, column index. So we are going to go to the row whose row number is 0, and the cell whose row number is 0, and whose column number whose column number is whose row number is 1, and whose column number is 0. So it's just this cell. c1 0, and then we're just going to put a 0 over here, and the next round we're going to increase I by 1, so I becomes 2. So we're going to go to the second the row the cell whose row number is 2 and whose column index is 0, so it is this one. Then we're going to make this number 3, so this becomes 0 4 0 5 0 6 0 and 7 0. Okay, so this is what we do with the first for loop, and then let's look at the second for loop. For j starting from 0 to n is 6. Okay, so we have c0j as 0. Okay, c0j as 0. So initially when j is 0, so it is c0 0 as 0. Okay, so c0 0 c0 0 is right over here, so we just assign 0 to here, and next we're going to increase j by 1, so it becomes c01 as 0. c01 is this cell, so we're going to assign 0, and then it becomes c02 as 0. So with this for loop we're going to assign zeros to the first row, and so this is what we do. And here I'm just going to ask you a question. Why are we going to assign zeros in the first row and first column of the array C? Why do we do that? Think about it. And this is because of this. Okay, Cij is 0 if I is 0 or j is 0. It means that C0j is 0, and also Ci 0 is 0. So like the first row and the first column here, C0j means that every value in the first row should be 0, and then Ci 0 equal to 0 means that for everything in the first cell in the first column should be 0. So this is just a direct translation of the first case in the mathematical formula. And then let's just continue. Okay, so with the main for loop of starting from line 8. So before that, I just want to ask you a question very quickly. Okay, so let's look at this one, this a matrix or a two-dimensional array. Okay, if I tell you this is Cij, this cell's location, its index is I and j, meaning that it's on the ith row and j's column. So where is I minus 1j, and where is I j minus 1, and where is I minus 1 and j minus 1? Okay, so where is I minus, so here we have 0. This is the row number starts from, assuming that the row number starts from 1 or 0, and then the column number also starting from either 0 or 1. Okay, so so where is I minus 1j? I minus 1j should be here, the row above, so it's going to be in the same column but one row above it, so this is above. See, and then what about ij minus 1? It should be to the left. Okay, this is ij minus 1. It should be in the same row but one column before it, so it should be on the left. What about so let me just let me just use another word, top. So okay, so what about I minus 1 j minus 1? It will be one row above and one column before, so this is I minus 1 j minus 1, so it is going to be top left. Okay, so this is the relative location between I minus 1 j minus 1, I minus 1 j, I j minus 1, and I minus 1 j minus 1. Okay, so with that in mind, let's continue. Oops. oops, I shouldn't have removed that, but I'm going to just write down a b c b d a b, x as a b c b d a b, and y as b d c a b a, b d c a b a, and then we have b d c a b a. Yes, correct. And then we have m as 7 and n as 6. Okay, so so here let's look at the for loop. Okay, for i equal to for i starting from 1 to m, so m as 7 and for j starting, so here we have I as 1, and for j starting from 1 to 7, and j starting from 1 to 6. If xi equal to yj, so if xi equal to yj, let me just put x over here. So I'm going to write down every character in x over here. Okay, so a, b, c, b, d, a, b, and y is going to be this. Okay, y is going to be b, d, c, a, b, a. Okay. So also I'm going to write down x and y right over here. So we have x as a b c b, a b c b d a b, a b c b d a b, and y over here as b d c a b a. Okay, so here we're just going to compare x1. So we have x as, I'm just going to use a different color. We have x as 1 and j as 1. So if you remember, we usually use x and y as the index, right? So here we do use x as the row index, while j as the column index. So okay, so here so initially we have both x and y as 1, so they just point to the first row and first column. Okay, so if xi equal to yj, so we have xi as a and yj as b, so they are not a match, so this is false. Then we are going to the else. If say I minus 1j is larger than or equal to say ij minus 1. So here let's take a look. I'm just going to use a different color, use the blue color. Okay, so if say I minus 1j is larger than say ij minus 1, if I tell you, okay, this is say ij, this is say ij, and it compares say I minus 1j and say ij minus 1. Say I minus 1j is here. Okay, this is say ij minus 1, and then this is say I. So this is say I minus 1j, and this is say I. This is going to be say I. I'm just going to use blue color for this one, for say ij minus 1. This is say ij minus 1. Remember that if this is say ij, then say I minus 1j is on its top, while say ij minus 1 is on its left. So this is going to be this is on the top we have say ij minus 1, and on the left we have say on the top we have say I minus 1j, and on the left we have say ij minus 1. So they're both 0, so this is true. And what we do is that we just assign say ij as say I minus 1j. So it's like we copy the value from the top to this cell. So this cell has a new value. This cell has a new value as 0, which we got from its top. And then we're just going to put bij as up. So here bij meaning b11. So we're going to put an a top sign at bij. Okay, meaning that we got the value from its top. We got the value in C from its top. And then so we're just going to start another for loop with j as 2. So we move j 1, we increase j by 1, so j becomes 2. So j is here. Okay, j is here. So now we're comparing xi and with yj. So we have xi as a and yj as d. So they're not a match, and we're going to go to the else if. So we are going to compare. So Cij is here, and Ci minus 1j is on its top. Ci minus 1j is on its top. I'm just going to remove this one and this one. Okay, Ci minus 1j is on its top, while Cij minus 1 is on its left. It's on its left. It's right over here. Sorry. So again, they're the same. So they're equal. So this else if statement is true, and then we're going to execute the same. We copy the value from its top, from Ci minus 1 j to Cij. So we're just going to get a new value in this cell from its top, and then we're going to put an upper sign at its left. So in the corresponding cell of B, meaning that the value comes from its top. And then we're going to increase j by 1. So j goes to 3. J goes to 3. So we're comparing xi with yj. So xi is a and yj is c. So they're not a match. Again, we're going to do the same thing. And so here we have Cij as here, and then Cij as here, and Ci minus 1j to its top, and Ci j minus 1 to its left. Okay, so we're going to compare these two values again. So it's the same. It's the same value. So we're going to this else if statement is going to be true, and then we're just going to copy the value from the top to it, and so we're going to put an upper sign over here. Okay, so next we're going to increase j by 1. J goes to 4. J becomes 4. J is here. Okay, J is here. So now we finally find a match between xi and yj. So between the two characters, they're both a, so it's a match. So in case it's a match, what we do is that we get the value from its top left, which is from Ci minus 1 j minus 1, and top Ci minus 1 j minus 1 is at the top left. So we just got the value from the top left and add 1 to it. So here we got a value which is 1, because the value comes from the top left, this 0, and then we just add 1 to it. Okay, so then in the corresponding cell of B, we just put an upper left sign. Okay, so next we're going to increase j by 1. So j becomes 5. J becomes 5. So xi remains a, while yj becomes b. So they're not. It's not a match. So then we come to. It's not a match. We come to line. We come to this line. This else if. So we're just comparing. We're just comparing its top left with its top with this left. Okay, so Ci minus 1j is 0, while Ci j minus 1 is 1. So this cell is 1. So it's false. This one is false. So we're going to come to here. Okay, to the last to the else. We have Ci minus 1, Cij equal to Cij minus 1. Cij minus 1 is to its left, so we're going to copy the value 1 from its left and put a sign, put a left sign in the corresponding cell of B, meaning that we got the value from its left. And then we're going to increase j by 1, so j has a new value which is 6. So again, here we are when we are comparing xi with yj, is a match. It's a match. So we're going to go to execute this section. Say say j equal to say I minus 1, j minus 1 plus 1. So we're going to get the value from top left, and add 1 to it. So we're going to get the value from top left, which is here. So we're going to get this 0 value and add 1 to it. So we got 1 at this cell, and then we have a top left to in the corresponding cell of B. So okay, and then we just finish. So J already reaches its maximum value. So then we go back to the outer for loop, and then increase I by 1. So I becomes 2. So we have I as 2. I is 2. And then we restart the inner loop, starting from j equal to 1. So j starts from 1. Okay, so here we have xi as b and yj also as b. So this is a match. And when there is a match, according to what we do previously, we just get the value from top left, add 1 to it. Okay, so then this value becomes 1, and we assign top left to the corresponding cell, and then we increase j by 1. J has a new value, which is d. Okay, j is here, so yj is d, so it does not match xi. It does not match xi, which is b. So let's look at this part of the code. Okay, if say I minus 1j is larger than or equal to say ij minus 1, say ij equal to say I minus 1j, and otherwise we have say ij equal to say I minus 1, say ij minus 1. So can we say it in this way? Say ij is going to be the max between say I minus 1j and say I j minus 1. We can say this because when this value is larger, then we're going to assign this larger value to it. Otherwise, we're going to assign, again, the larger value to it, okay? So yes, so say I minus 1j is going to be the maximum value between its top, which is say I minus 1j, and its left, okay? So in case there is a mismatch, we're just going to grab the value from its top and the left and see whichever is larger and assign to say ij. So here, when we're working on this cell, we found, okay, its top value as 0, its left value as 1. So obviously, its left value is larger. So we are going to assign the larger value to it and put a left sign over here, because this means that we got the value from its left. And then we increase j by 1. So then let's work on this cell. We increase j by 1. J is here, so it's a mismatch. And then we're going to compare the top and the left. Obviously, left is larger, so it's going to be 1. And left. So I'm going to repeat this procedure. And then we increase j by 1. J goes to here, and then so it's a mismatch between xi and yj. So we're going to compare top and the left. So both top and the left here are 1. They're both 1. In case there is an equal, we got value from top. We prefer top. Okay, so we just got value from top. And then we increase j by 1. J goes to here. Okay, so so we have xi match bj match yj matches yj. So then we, in case there is a match, we just get value from top left and add 1 to it. So we just get a value from top left, which is here, add 1 to it. It becomes 2. So put a upper left sign over here, and then we increase j by 1. So it's a mismatch. And then we're going to compare its top and the left. Obviously, left is larger, so we get a value from left and then give a left sign in B. So then we're going to work on the third row. So we have we increase I by 1. I becomes 3, and xi becomes C. So we restart J from the beginning. just restart J from the beginning. So here we have xi as C and yj as B. It's not a match, so we're just going to compare top and the left. So we obviously top is larger, so we got the value from its top, and then so put an upper sign over there, and then so we're going to increase J by 1. J comes to here, so C and D is not a match. C and D is not a match. So we're going to compare top and the left. They're equal, so we get the value from top. So next we increase J by 1. So yj is 3. Okay, so now it's a match. We just get the value from top left. From top left, which is here 1, and add 1 to it. So and then we're going to increase J by 1. So yj becomes A. So it's not a match. Then we're going to compare. Let me say top and the left. So obviously left is larger. So we got we copy 2 to it, and then we increase J by 1. Okay, so it's not a match. Then we're just comparing top and the left. So they're equal. So we got value from top, and then we increase J by 1. So it reaches here, and then so it's not a match. We're going to compare top and the left equal. So we got value from top. Okay, so next we're going to work on the following line with I and J. So in the beginning we got a match, so we got a value from top left of 0, add 1 to it, so it becomes 1. Let me make it clear, okay? And then we increase J by 1, and it's not a match, so we're just going to compare top and left. They're the same, so we're going to get the value from top. And then we increase J by 1, so it becomes, so we're just going to work on this cell. It's not a match, so we're going to get the value from top. Let's look at this cell. B and A is not a match. B and A is not a match, so we're going to compare top and left. Same, so we got value from top. And then let's work on this cell. So we got B from X and B from Y is a match. So we got value from top left and add 1 to it. And then here we're going to work on this cell. It's not a match, so we're going to compare top and the left. Left is larger, so we got copy value from left and assign a left sign. So then we're going to work on this cell. Okay, we're going to work on this cell. So we have a mismatch. So we compare top and the left. Top is larger. So, and then here is a match. So we got value from top left. So add 1 to it. Here, this is not a match. So we compare top and the left. They're the same. So we got value from top. And so here we're just comparing so A and D is not a match, and then we're going to compare top and left. Same, we got from top. It's not a match, we got value from top because top is larger. Here it's not a match, so we got value from top because top and the left are the same. So here we got a mismatch, so we got value from top. Here we got another mismatch, so this is another mismatch. And then here we got a mismatch from top. It's a match from, so it's going to be 3. And then here it's not a match, so we're going to get a value from top. And then here we're going to get a value from, it's a match, so we're going to get a 4 top left. So here this is a match, so it's going to be 1. Here it is a mismatch, so it's going to be 2. It's a mismatch. And here it is a mismatch, so here it is a B and B, it is a match, so it becomes 4. And here we got a, let me say, here we got a mismatch, so we're going to get a value from top. Okay, so then we just finish this for loop. After we finish this for loop, let's say how, so here it asks you to return C and B, but let me ask you one question. Do you know where can we find the length of the longest common subsequence between x and y? Yes, it's over here. It's at the right bottom corner of the array C, because the right bottom corner means that CMN means that the first the length of the longest common subsequence between the first m characters of x and n characters of y. It's like it's the length of the longest common subsequence between all characters of x and all characters of y. So that is why this style tells you the length of the longest common subsequence. But some of you may say, okay, what is the longest common subsequence? And this will depend on the array B. So here, if starting from the bottom right, we can just follow the sign. Here we go left, and then we go upper left, and then we go up. And here it is a upper left, and so left. After we go left, it is a upper left. It's an upper left and a left, and an upper left and up. So this is the route for us to go from the bottom right to the top left. And here, let's say how many top left arrows or upper left arrows have we seen? So we see one upper left arrow here in this route, another one, and another one. Okay, so we see 4 upper left arrows. So let's say the characters in the characters for the upper left arrow. So we got A for this one. Okay, for this one we got A, and for this one we got B, and for this one we got C. For this one we got B. So B, C, B, A. B, C, B, A is the longest common subsequence, and that is how you reconstruct the longest common subsequence from the array B. Okay, so this is the whole procedure. Okay, and with this function you will be able to see you'll be able to print out the longest common subsequence. So, but this is not necessary in your homework. As long as you figure out this number, it is fine. So okay. And for some of you, so here, I think for some of you, the question in your mind is, how do you implement this upper left and top and left arrow in Java? And actually, you can replace them by 1, 2, 3, because here you only need them for comparison. If it's a top left, or if it is a upper left, if it's a top, or if it is a left. So we can just use constant to replace top left, and up. So whatever you want. And actually in your homework, so you can totally forget about B. There is no need for you to create the array B, because I'm only asking you for the length rather than the longest common subsequence. Okay, so you don't need to worry about B, the array B. And the other question I want to briefly talk about is the complexity of the algorithm. Here, as I previously told you, okay, when we want to infer the complexity of an algorithm, we only need to pay attention to 2 parts: function call and loops. Here in this function, it does not call any other function, so there is no function call, so we just need to focus on loops. Here we got the first loop over here. How many iterations are there in the first loop? M, because we're going to increase I from 1 to m. How many iterations are there in the second for loop? N plus 1 for loops, because n plus 1 iterations, because we're going to increase j from 0 to n. And then here we have a nested loop. So for this nested loop, for the outer loop, there are m iterations, and for the inner loop, there are n iterations. Okay, so here, because this is an outer and nested loop, so we need to calculate the total number of iterations. We just need to multiply those two numbers together, and then for these three for loops, because they are just parallel, so we just need to sum them up. So the total complexity would be of this algorithm would be m plus n plus 1 plus m times n. So the dominant factor is here, m times n, so we only keep the dominant factor, and that's why we got the time complexity as OMN. Okay, so the time complexity of the longest common subsequence problem is OMN, where m and n are the length of the input strings. Okay, so yes, this will be the whole part of the lecture. I strongly encourage you to read chapter 15.4 to have a better understanding of dynamic programming, especially for those of you who want to be a software engineer. According to my, as I said in the lecture, according to my previous experience, dynamic programming is the challenging point, which decides if you can find your first software engineer job or not. Okay? So be serious with that. You don't want to regret. All right, so this will be the lecture for today, and thank you. Have a nice week.